Hello? Hello, Professor C. Can you hear me?
Hi. Yeah.
Hi. Okay. I suppose we can wait for a couple of minutes because George promised me to join with his iPhone.
Sure.
Okay.
Hello, I'm here. I think we can wait for another couple of minutes before we start. I'm sorry
Okay.
for some delay. I'm actually not
that's
at
fine.
home, and I'll briefly
That's
come
fine.
back home and I change my account a little bit. As a matter of fact, Pavel has confused online and offline, so he was waiting for us in the independent university. So I wonder, he'll probably join us soon, but I think we can start already. Okay. Please, Yuan-Chen, check if you can share your screen with us.
Okay, so let me try this. Okay, sure. You can see my screen, right?
Yes, we can see it pretty well. Thank you.
Okay, great. Thank you. Okay. So we can start now?
Yeah, I think we can. But I don't know if Pavel will join soon or not, because he said he was waiting for us in the university and not online.
Okay.
So,
So both are, both are
yeah,
okay.
he was.
So
Yeah, so it's my pleasure to introduce today's speaker. It is Yuan-Chen Xi from Beijing University, Beijing International Center for Mathematical Research. And he has made a talk at our seminar last semester. Last semester he spoke about some models in integrable systems, but today, on my request, he will talk about full constant order lattice. That's part of his paper published in the end of last year, and I think we can discuss this because I really like order systems. Okay, please begin.
Okay. Thank you for the invitation of Professor G.I.Шарыгin, and also it's my great pleasure to give another talk in this seminar. So this time I will talk about the full constant total lattice, and so several weeks ago, Professor G.I.Шарыgin actually talked about the full symmetric total lattice, and this one is actually parallel to that one. And my talk will be divided into 3 parts. And the first part, I will help us to recall some basics, including like the relationship between symmetric total lattice and the constant total lattice. Okay. The second part, I will talk about what's the full constant total lattice, and also its singular solutions. So like this is our main concern. And the third part, I will talk about like a very old method, Kowalewski-Panevet analysis. Okay, so let's begin from the very elementary stuff. So the classical finite open total lattice is this kind of a Hamiltonian system. So when we talk about the Hamiltonian system, so we need to give you 2 things. The first is what's their Hamiltonian, and the second is their Poisson brackets or their symplectic structure. So their Hamiltonian looks like this. So you can see, let me see. Okay, so the first part is their kinetic parts, and their second part is their potential. Okay, so this says that only their nearest neighborhood, there are 2 particles in their nearest neighborhood, they have a exponential potential. So their symplectic structure we use is just simply their symplectic structure on R2n or C2n in so depends on their field. Okay, you consider, and with that, then we can write down their Hamiltonian equation. So their Hamiltonian equation further, you can just write down it like this. Okay, so this is a nonlinear system, and normally we don't expect that we can write down. So we can know much about the nonlinear system. So, but in 1974, so Flask made the following change of a variable. So he let AK to be -1/2 over PK, and the BK is this exponential expression. So then the original system written in terms of AK and BK, you can just write it in this way. So then he observed that, of course, like your Hamiltonian also have a simple expression. Then he observed that if you write it in terms of AK and BK, then actually you can put it in Lux form. Okay, so here LK is just a symmetric matrix that you put AK on the diagonal and BIs on the off diagonal. So L is symmetric, And here so the other term in our Lux pair is the pi L of t, that's the skew symmetrization of L. Okay, so you just make a you just take the skew symmetrical part of L out and then take the commutator. So this is just the usual commutator. The commutators of AB is AB minus BA. Okay, and then so when we write down Lux form, then we already know a lot of information of this system. So in particular, so this system is integrable because according to this expression, and we will also explain it later again. So according to this expression, actually already know that all the eigenvalues of L of t so are preserved. So that means we have actually so n-1 conserved quantities, and their phase space is 2n, 2 times n-1. Okay, because we also put a restriction on the trace that we require the sum of trace is 0. So in 1979, in a very influential paper of Constant, so he did something like this, or so we can understand his theory like in this way. So this is our original L matrix. We can conjugate it by a diagonal matrix, and then we get another matrix Y in this form. So so we can, and then if we just write down like look at the equation for x of t, which is just 2 times y of t, then x of t actually satisfies the following Lux equation. So here the x bigger than or greater to equal 0 is just the upper triangular part of this matrix X. Okay, and the x minus 0 is just the lower triangular part, and you put all the other entries to just to be 0. So if we just compare this expression, we see that you see if it's so if y comes from the conjugation of L, then we know that the off diagonal are squares. So if we consider this in the real field, and we would require this to be positive. Actually, there's another simple way to get constant lattice, total lattice. So we begin still from the Hamiltonian system. That's our system 1. So this is the 1, and we make a changeable variable very similar to Flask's changeable variable. So we let AK equals just negative PK, and BK equals the exponential term. And then the original system actually can be put in this way. So the Lux form, and here L here is just a Jacobian matrix. So here L bigger than or equals to 0, L minus 0 is the same thing that we defined before. So in this form, if we put it in this form, actually we see that this makes sense. So this equation makes sense for any BIs. Okay, I mean, if we consider it under complex plane, and so this says like we can make it negative. So writing in this way, actually everything gets a meaning in Lie algebra. So next, let me introduce some notations in Lie algebra and Lie groups. So most of the notations are standard. G is a simple Lie algebra. H is so you just take a Cartan subalgebra, and also n plus minus, that's a nilpotent subalgebra, Borel subalgebra. So pi is a set of simple roots, and data plus minus are the set of positive and negative roots, respectively. Omega I here is their fundamental weight. So for each of their fundamental weights, we can construct a fundamental representation, which we will use later. And H alpha I, X alpha, Y alpha, they will consist of a Chavalit system for this Lie algebra. And their following ones are their corresponding Lie groups. For example, G is the Lie group of a G. We can take it, so for simplicity, we can just consider their connected and simply connected ones. And H is their Lie subgroup of G, whose Lie algebra is H, and so n plus minus, b plus minus are the same thing. So basically are the Lie groups of these guys, and W is their well group. So when we have this, then we can just interpret. So there this Lux matrix in Lie algebra terms. So these guys, they are just their summation of a positive simple root vectors, and AIs. So here we can put it as coefficients of the Cartan. Okay, so this is a type A theory, and this is a concrete example. And BIs, so this corresponding to the coefficients of simple negative root vectors. So matrices like this, we put other matrices like this together, and that will give us a Jacobi variety. And then the constant totalities, we can define it similarly like this. So this is the projection to the Borel. That means you just take the upper triangular part of L if you choose your coordinate properly. Okay. And the equation, constant totalities equation, actually we can put it in this form. So there, here CJK is just the Cartan matrix of this Lie algebra, and their Hamiltonian is just 1/2 over the trace of L squared. Okay. Now that means actually we can consider similar stuff on Lie algebra, all simple Lie algebras, and now we can see why all of them are just give us integrable systems. Okay, so this comes from the factorization method. That means that we just take a initial matrix, so L0, that's the initial condition. So our goal is just to solve this system. Okay, so we take an initial condition, that's L0, and we take the exponential of TL0, and we decompose it into the product of n minus of t times b plus of t. So this is just the lower triangular matrix, unipotent matrix, and B belongs to the upper Borel. So this is our just the classical Gaussian decomposition, or people call it LU decomposition. Okay, and notice that when t equals 0, so this is an identity matrix, and you can always do the decomposition like this. And when t is small, so sufficiently small, this decomposition always exists. Okay, so because you're just in a neighborhood, small neighborhood of identity. So if you write it down like this, then actually we can write down the solution L of t. So it's just the adjoint action of b plus t of t act on L of 0. So this shows you explicitly that the eigenvalues of L0, they will not change. Okay, and for simple Lie algebra, so for simple Lie algebras, we can use another term like so this action preserves all the Chauvet invariants. So this is nice because literally we solved the original equation, but the drawback is that, okay, so this decomposition is not easy. We don't want to have this decomposition for you see when L0 is large. So this basically says like you need to do LU decomposition. Basically, so it's quite complicated, especially like you want to write down like b plus b plus of t as a function of t. So Cosner actually introduced another. So another way to give us the solution for this system. So as we said before, omega j is just their fundamental weights. So for each of their fundamental weights, we can introduce a fundamental finite dimensional fundamental representation for the Lie algebra G. So rho omega j is a representation, and v omega j is their module. And we assume that so we can find their highest weight vector. So we take their highest weight vector, like small v omega j, and then we can define their so-called tau function. So tau function is something like this. We can always choose on this module. We can always choose the inner products that is invariant under the so for the closed form of a compact form under the compact form of G. Okay, and also we can require that this this metric has the effect that like you take a conjugation and then x alpha goes to y alpha. Exponential of x alpha goes to exponential of y alpha. Okay. So all you need to do is you can use just a unitary trick to make this metric to have all these nice properties. And then so this just means what? This means we use our exponential matrix act on the highest weight vector, and then we pair with its highest weight vector. Okay, so tau function is nice because in this form, you don't need to decompose their exponential function, so they're group elements, and it's basically like calculating exponential is not that bad. You can just put it in the in a computer, and it can do it. So the computer can do it for you very quickly. And this just says you just take the proper generalized minor or matrix coefficients of this matrix. So and this definition is always also nice because you see there's no dynamic system in this definition at all. We just need to use representation theory of their Lie algebra and their Lie group.
I'm sorry.
Mm-hmm.
Well, this exposition assumes that there is a unique fundamental module with the highest weight vector of prescribed weight. Is it always so? Is it some additional assumption that you make?
It is so. So for each of their fundamental weights, you can construct a fundamental module with that high, so with the highest weight vector. Actually,
but is it unique?
Unique, yes. And also we can. I mean, this guy it's not unique, but we can also put some restriction. For example, we can choose their we can choose their metric. After we choose their metric, we can require v omega j and v omega j. So it's 1, and that will just fix this highest weight vector.
I see.
Okay, thank you. So any other questions?
Not from me, but I just asked what I felt was a little bit. I didn't understand something. Then I asked.
Okay. So this is unique, and actually Katan already constructed other fundamental representation for other simple Lie groups. So so you see this part only involves the representation of this Lie algebra and the Lie groups, and remarkably, so it actually like solves their original system. So that means Aj actually can be expressed in terms of the tau of J, and Bj can also express in terms of tau of J. So so that's the story of constants. And the next thing that we learn from this theory is that, okay, so from the factorization method, we see that this is actually a group element B plus, so acts on L0, okay. So actually, according to the theory of constants, so total lattice should really be viewed as the co-adjoint action of the Borel subgroup act on its co-adjoint orbit. But there are actually several ways to realize this B plus star, so the co-adjoint space. For example, like in type A for SLN, and we have two different decompositions for generic elements in this group. Okay, so one of them is just a QR decomposition. That means you decompose an element in this group as a orthogonal group element and upper triangular elements. And another decomposition is a Gaussian decomposition. So Gaussian decomposition is actually just for a generic element. Okay, but the QR decomposition actually is for any element. So that means we can actually use a Killing form to identify B plus star with either the linear space of symmetric matrices or the affine space with lower Heisenberg matrices. Okay, so the former will give us a symmetric total lattice, and the latter will give us like constant total lattice. So so what we want is, of course, like study, as this is the co-adjoint action of a B plus act on its co-adjoint, so act on B plus star. So there are many different symplectic leaves inside B plus star. And one question that you can ask, so actually there are three diagonal total lattice. As we now understand, it's the smallest, minimum indecomposable co-adjoint orbit, which has a regular element, it contains a regular element. Okay. Now we can ask ourselves the question like, what about the other simplex leaves? So the other special simplex leaves that we can consider is the generic one. That's the one which has like the biggest dimension. Okay, so the one with biggest dimension, we call it a full constant total lattice, and it has the Lux matrix in the Heisenberg form. That means, so in type, for example, in type A, so three diagonal total lattice, we just have a three diagonal to this part, but for constant total lattice, we extend it to to other for other metrics in the Heisenberg form, and for other Lie groups, Lie algebra, we can do the same thing. So this is what we call the full constant total lattice. Okay, so when we after we cook up this kind of a system, the first question we need to ask is, how much we can understand them. So actually, we can many things. It turns out that like many things we worked for three diagonal total lattice still work for full constant total lattice. For example, we can still use the factorization method. That means like we take initial condition L0, except that so the only difference is this. Okay, for three diagonal total lattice, L0 is a three diagonal matrix, and for constant total lattice, you can just take any lower Heisenberg matrices, and you just put it here, and then you decompose it. So do the factorization, decompose it as a product of a lower unipotent matrix and the upper Borel matrix. Okay, and then you can just write down like their solution. So this is easy to prove. You just first you notice that when t equals 0, okay, so we can define this guy by this expression, and when t equals 0, this guy has the same initial condition as our guy that we want to solve, and you can also check that this guy satisfies the same differential equation, like that. So that will show you that actually, so this is a solution of the full constant total lattice. Okay, still we don't like this one because we still need to do their factorization. Their factorization in general, it's quite complicated, and we want something that's like a tau function. We don't need to do their exponential. The other thing is that, so from this expression, we know that, so their flow will preserve their eigenvalues of L0 or their Chauvet invariance of L0. So that means that their total flows will evolve under isospectral variety defined in this way. Okay, and just like Professor G.И.Шарыгin explained last time, therefore constant for symmetrical total lattice is integrable. Therefore, constant total lattice is also integrable. So their procedure, their proof is basically the same. Okay, so we'll just recall like their how you construct their additional invariants in type A. So in type A, you just do the same thing as for symmetrical totality. For symmetrical totalities, you take their your Lux matrix and consider its eigen matrix, and you take out. So this symbol means you take out the first k rows and the last k columns of this matrix, and then you calculate its determinants. So its determinant will be a polynomial of lambda of degree n-2k, and their invariants that you get are all, so other I 1k, I n-2kk. So these are their invariants. And you take k from 0 to brackets, so n-1 divided by 2, that many. So that pretty much gives you half of the dimension of their whole space. Okay, of this like isospectral varieties. I mean, these are their Chauvet invariants. They're always there. So that actually gives you the integrability. And what we want is we want to know more. So we can actually construct its solution. So we just do the same thing. We define the tau function, and we play a similar game. We put an exponential of t L0 here, and this is the highest weight vector, and this is the same matrix, satisfies the same condition, and then we can show that. So you just take the log and take the derivative. You will get an expression for the diagonal elements. Okay. And this is also based on the assumption that t has to be small enough, because we actually, this proof actually depends on the factorization method, and we know that when t is small enough, this factorization can be performed. So and actually we would like to understand more about the properties of the solutions. Actually, you may worry about like this is good enough. So if we just know the diagonal elements, so how do we say that we solved this system? Actually, we can show that all the other elements can be expressed in terms of a tau function. I will show you later in an example. Okay. So the other thing that we want to understand is about the properties of this solution. So there's a theorem of constant. It says we can do something like this. So we can choose an L-dimensional linear space in B minus, such that we can just use the lower unipotent group conjugate an element in E plus S. So E is just the sum of their positive simple root vectors, and we can use the lower unipotent group to conjugate it and get other, so this is the Heisenberg matrix that we were considering. So this is an isomorphism of our affine varieties. So we can play a game like this. Okay, this is for any. So this is an isomorphism of finite varieties. That means like any matrix on this side. We can also use elements in the lower unipotent matrix to conjugate it into their normal form. Okay, so this x e plus s. This is in the literature. This is called their constant section, or it's so in singularity theory, it's also called the Slowdown section. Okay. So then we can play another game. So you see, we can just take any matrix in their Heisenberg form, and the theorem of constant tells us we can use a lower unipotent matrix to conjugate it into a canonical form. So C lambda belongs to E plus S. So this is the constant section. Okay, and then this, so we can view this U as an element in their flag variety. So that's G modulo B plus. Okay, because U actually belongs to N minus. So this says what? This says U actually belongs to their big cell of their flag variety. So with this embedding, we have their following diagram. So we can take the initial value of L, that's L of 0, and we use U0. You actually use your inverse to conjugate it into C lambda. We know that C lambda belongs to E plus S, and S only contains, so it has dimension L. Okay, so this L dimension actually only contains the information because it's a conjugation. Okay, so it only contains the information of Chavalit invariant, or put another way, like the eigenvalues of our initial condition. Okay, so then we view this as an element in the flag variety. Since on this side we're using the UT of inverse to conjugate, so our solution is from the factorization method. Our solution is actually obtained from L0 by you just conjugate another unipotent matrix which depends on T. Okay, so that means on this side, actually, for L of T, we want to get C lambda. We need to use this guy, the inverse of this guy, to conjugate L of T to the form C lambda. And then we because B plus, from B plus we can just bring out any any element from the upper Borel. So we can just bring elements B, so U of T times B of T, that will give us like exponential T of T times L0. And we know that so L0 and C lambda are related in this way, and this will give us the next one. Okay, so from here we see that why we want to do this embedding into flag variety. Our initial condition, initial point, so this is our initial condition, and we embedded it at a point like U0 B plus, and this is a tilde flow. Actually, this is on this side on the flag variety. What it says is this. Okay, so basically it says D. So if we just look at the evolution of U0, so du dt is just exponent. Du dt is just C lambda U. So this is our linear flow, right? Because you have your initial condition here, and that's your solution. That's linear. So this actually means the full constant flow actually linearized on the flag variety. And then
I think that's pretty much like the symmetric flow, right?
Yeah. So this is actually, I mean, for in integral system, what we do is just inverse scattering, right? So this is the scattering. And this is the evolution, which is a linear flow. And then you inverse this guy, you get your solution. So this is exactly like their inverse scattering method in this simple example. Okay. So so what actually we really want to study is something like this. Here we notice that it has a very serious restrictions, because according to the theorem of constants, we can only get information in their big cell. That means that this U is actually like in their big cell. So it's in n minus, and U of t also in n minus. Okay. But we want to study the geometry of the solution. So that means we can imagine something like this. There is we consider everything in a complex plane. So that means our t can be any complex number, and when their previous thing doesn't so their factorization, we know that their LU factorization. I put it here. In particular, I put here a condition when t is small enough. So this factorization we can take. Okay, but when t is big enough or somewhere, then this factorization might fail. That means this flow may leave their big cell and goes to their a small cell. And we know that so there's a more general factorization than LU factorization. That's the Broad decomposition of this Lie group element. So imagine that there is a T star in C such that we couldn't perform their LU factorization, and then we need to use their more general one. So U star is still a lower unipotent matrix. B star is a an upper invertible upper triangular matrix, and the W star is an element in the while group, and I put a dot here to show to signify that it's a representative in the Lie group, any representative. Okay. So this means that at T star equals 0, and we couldn't perform their factorization, then our previous method just fails. Okay, so this is a singular point, and we call this kind of point Panevet divisor. So we want to study the singular behavior of the solution. So what we can do, we just take so since this flow is linear on the exponential, we just take translate it to this point. Okay, so this part is this T part, and this part comes from the T star. So at T star, we just decompose it into this guy, and we put it here. Now we note that this is the highest weight vector. That means their upper triangular matrix, their positive Borel, it acts on their highest weight vector just by a constant dk. Okay, and then we can just take their constant out, and this is their lower unipotent matrix, and we can flip it to this side. I said before, so so this is their metric. If it's a joint, so there are joints of exponential x alpha. So the joint of this is exponential of y alpha. And this, sorry, so this is a y alpha and this is x alpha. Okay, so that means that when you flip this to that side, you get you still get an element in their upper unipotent matrix, and that acts on their highest weight. That's just a 1. Okay, so this also goes away, and we can combine this guy with that guy since they're both of them are lower unipotent. So let's write it as U. Then we get an expression like this. Okay. So now the problem, the question we want to ask is the following. So from the constant theorem, we only have the information for their big cell. We want to understand what kind of singularity their tilde flow can develop. So that means like which lower Broad cell we can hit. So in terms of this expression, equivalently, we want to understand what kind of U and what kind of a W star we can put there. So then we still have a solution for the totalities, for constant totalities. And of course, you can imagine, and this is actually we're going to prove. So the best, so the ideal situation is, I don't want any condition on U and any condition on W star. And that's going to be our main results. So in some sense, you may take it as for granted because of what? Because of you see the dimension of U. So as we said, like so the total flow, it will preserve the spectrum of L0. Okay, so actually that takes out dimension by L. So that means the dimension of the initial condition, actually it's the dimension of a Borel. But L of them, they're constants, and so this has just exact the right dimension that we want. But I will show you that so even though this result looks natural, you shouldn't take it for granted. I will so give you two reasons why you shouldn't take it for granted. So one reason is that I will explain it later. Okay, in concrete example that will be like a better understood. So I will show that you can actually take any U and any W star here by a local analysis. So this local analysis is called Kovalevsky-Painlevé analysis. That's actually a method exists like for more than 100 of years in the group system. And this is actually a nonlinear Frobenius method to solve a linear ordinary differential equation. So let me explain what's Kovalevsky-Painlevé analysis. Okay, so this is actually quite straightforward. So we don't need any advanced knowledge to understand this method. So basically in the sense, we want to solve a nonlinear differential equation. So okay, then we assume the solution looks like this. Okay, and the first thing that we want to identify is we want to identify like what's their exponent. So delta I, alpha, gamma alpha, and what's their initial so leading coefficient. That means AI0 and B alpha 0. Okay, so after we have this kind of information, and then we can just plug this series into the system of equations, and then we will find we can find the coefficients recursively. But at some point, you may have some kind of problems. That means like you couldn't you couldn't solve their equation uniquely. So if you encounter that, then there's a point that we call the resonance. That means you have to introduce like 3 parameters here to be able to solve this. So continue this iterative procedure, and at last so after you get out get other coefficients, okay, and then you get a Laurent series in general. And then you need to check that compatibility condition. So this is actually a Fredholm type of condition. I will explain it later where this comes from. And also you need to show that so this solution actually they converge. Then you indeed get some meaningful result. Okay. So in order to, I mean, this is a kind of so computation method. So let me explain it. There are other procedures just with one simple example. Okay. So let's look at this four constant totalities defined on SO5. So this is an example that we can still do it by hand, and then we can see like other structures. So here we have a free permit. So we have like our variables A1, A2, B1, B2, C1, D1. Okay, and if we write down their Lux equations out explicitly, so it looks like this. That means we have six equations. Okay, so we want to solve these 6 equations, and normally this is the last thing people want to do. So you have a nonlinear differential system, and you want to solve this nonlinear system. But before we do that, let me explain like something that I left out before. So I left out like initially I told you the elements on the diagonal can be expressed in terms of a tau function. Okay. Then from this explicit equation, you can see that. So we know A2 and A1, actually we know B2 and B1. After we know B2 and B1 and A1, A2, actually we know C1. After we know C1, then we know D1. So that means at least I showed you in this very concrete example that if you know the elements on the diagonal, you know everything. Okay, so that means tau function indeed contains other information that we want.
So is it always so for all classical systems, for all classical the algebras?
Yes. So this is quite different from the four symmetric totalities.
Yes.
You can, I mean, there you can still find the expression for the diagonal elements, but it doesn't have the other structure. You know the diagonal elements, so you couldn't deduce the other elements.
Yeah.
Okay. Yeah. But for four constant totalities, so you have this kind of a property. The first step, as I said, you need to identify the form of the solution. Okay. So that means we need to know where the solution begins. So this is a different for the linear differential equation. This is the essential difference between linear differential equation and nonlinear differential equation. In the linear differential equation, we have the Frobenius method. Actually, the Frobenius method actually tells you your initial equation actually tells you what's exactly the exponent there. But here we need to use other method. So this is called like you can balance their leading singularity. Just compare. Okay, so you just plug this type of the series into this equation, and then you compare both sides, the worst singularity on both sides, and then you come to the conclusion. So I will not show you the details, but you can do it. Okay. So that means like the elements on the diagonal, it has only simple poles at most. So the coefficient here can be 0. Okay. But what I mean exactly is so at most you can have simple poles, and this at most you can have a second order pole, third order pole, and fourth order pole. Okay, you can also deduce. I mean, from here you can deduce that these other guys. So that's the first step, and actually not finished yet. We also want to know what's the leading coefficient when k equals 0. Okay, so when you plug this series into the equation that we write down before, so this system, we actually get 6 equations for the leading coefficient. Okay. Now we need to solve this leading. So we need to solve these equations, and here is a way that how you solve it. Okay. So first, you see from the first 2 equations, we can just plug into the third and the fourth equation, and we just use these 2 equations we can kill. C10. Okay, that will tell us, give us a equation, a quadratic equation for A10 and A20. And from here, either of this expression, we can get an expression for C10, and we just plug it in here. We get D10, and we plug it into there. We get another equation between A10 and A20. So here are other equations. Okay, there are two equations that I told you. So a simple observation, their first equation is quadratic. Their second equation, it has degree 4. So that means in general, we expect 8 equations, by 8 solutions by Berzou's theorem. Okay, and you can certainly solve this by hand. So you will get 8 solutions, and if you stare at these 8 solutions, you will find something remarkable. That is like there are 8 solutions. All of them are positive integers. So so if you learn the combinatorics, or if you go to a seminar in combinatorics, you see people think very differently. If they see positive integers, they always want to know like what these positive integers count. So I will give you an explanation what they count. It's like this. Okay, this is kind of interesting. So you take a while group. So then their while group, we know that their while group act under root system. Of course, it also act under Q-root system. Okay, so you look at their action of a while group elements act under co-root system. And if their while group will map some positive co-roots into their negative ones. And also it will shop around their positive, some of their positive simple co-roots. But sometimes it maps their some positive co-roots into their negative ones. And this symbol means you just collect all their positive co-roots, which are mapped to the negative ones. And you take their sum, okay? And in this co-root system, you have some simple co-roots. So you can always write this sum as a linear combination of their simple co-roots. And from that, you will get a coefficient. And that coefficient actually solves this equation. So that means like these integers, indeed, they count something. So so here there's something interesting from a many perspective, because this is their while group act under Q-roots.
So which particular while element do you need to plug in into this?
Any.
I mean, but
so
then it means
I will show you. I will show you why any. Okay. So so
identity, for instance.
Yeah, identity, for instance. I will show you other things.
Okay.
But here we notice one thing. Okay. So how many? What's the cardinality of a while group element for SO5? Who knows?
I don't remember. Sorry.
Okay.
SO5 is it
8? Okay, 8.
So what was it? What was it? Is
so
it
their number?
what was the series? Is this A, B? Is it not A? It's B or C?
So it's B. It's B. Okay.
B.
B
right.
of rank 2. Okay. B of rank
B2.
2. B2. So their cardinality of a while group is 8. Okay. And the solution that we're looking for. So we're looking for 8 solutions. Okay. So that means for any while group, for each while group, you perform this procedure, you get 1 solution for it. And we have 8 while group elements that will give us 8 solutions. So in this concrete example, it means this. Okay.
So
this is their
is this
identity.
some kind of invariant of the group action? This polynomial? Is it some kind of model of polynomial for the group action or something like that? I don't know.
Yeah. So this actually you can put it in a very fancy way. Okay, because co-roots actually co-root system. So you have a co-root system. And that co-root system is a root system for another Lie algebra. And that another Lie algebra is the long-length dual of the original one. So actually this says, we're actually working for Lie algebra G, but somehow we need to go to the co-root system, and the co-root system is a root system for the long-length dual of G. So somehow long-length dual appear. But in any case, so you said like the identity element, right? So the identity element doesn't map any positive co-root into the negative ones, right? It keeps every positive root just to itself. Mm-hmm. So that means this set is empty. That means the right-hand side is 0. Okay. So that means 0, 0 is the solution that we were looking for, and 0, 0 indeed satisfies this. And another example. So let's take S1b. So this guy will just map alpha 1 check. So this is the co-root to a negative co-root. So so that means so I write it in this order. Okay. So A20, A10. So that means 0, 1 is a solution for this system. And you can check A20 is 0, A10 is 1. So so this is 0, 0, and this is 0. A10 is 1. That's a solution for this system. Okay. So you take 8 different while group elements, and you get 8 sum. So just take the coefficients. So this says 1, 0, this is 1, 2, this is 3, 1, 3, 3, 4, 2, 4, 3. So we have 8 solutions for these systems. And that's exactly the number that we want, right? Because Bozo's theorem says like this system has 8 solutions, and I give you a way to construct 8 solutions. Okay.
Is it always so? Just is it some theorem that you always get this kind of?
Yeah, I will write down a theorem later, but now I'm just seeing like we work out everything just on this simple example. Okay. So that actually solves our first step of Panavia analysis. Okay. So the first step I said that we need to identify their exponents, and we also need to identify their leading coefficient. Okay. So now what we want to do, so we have AI0, BI0, C10, D10, and we want to know what's AIK for K not 0, so bigger than 0. Then we can write down our differential equations in this way. So let's observe what's their. So the left-hand side are the B alpha, so AIK, BIK, they're things that we want to solve. And the right-hand side are the things we already know, okay? Because all of them are, we can solve from the previous step. Because I already told you their first step, their initial step when K equals 0. So now we can work on like how about K bigger than 0? So begins from 1. And so we look at this system, we find out that we can just write down it in this way. Okay, so this is actually like a K. So K is their exponent here. Let me see. So K is their exponent here. That's their step. K's step that we want to solve. But when we stare at this system, we see that actually we're just looking at a linear system. And here there's a matrix we call the Kovalevsky matrix. And this is their Kovalevsky matrix. So this is just says, okay, this is their eigenmatrix of a Kovalevsky matrix. And here are the unknowns that we want to solve. And on the right-hand side, these are the information we get from previous step. So that means we just need to begin from K equals 0, already solved, and to K equals 1. And after we know K equals 1, we can solve K equals 2. And after we know K equals 2, we we solve k equals 3. Okay, but here you see that this is a linear system. Then there are several things we need to worry about. First, so what if for some positive integer k, it's an eigenvalue of this Kovalevsky matrix, then this coefficient matrix is not invertible, right? And for that kind of a k, so we call it resonance places. That means at a k positive integer, let me spell it out. So if a k is a positive integer, spectra of a Kovalevsky matrix of this k, then this is not uniquely solved. Okay, so that means we need to introduce some free parameters to be able to continue this process. And another thing that we need to worry about is so if the right-hand side is not in there is not a linear combination of this column of this matrix, then you will have a problem. So this you need to put a Fredholm condition. That's the condition that I said actually in step 3 that we need to check. So remarkably, actually we can calculate their determinant of this this matrix explicitly. As we said, like so this will depend on the first step initial condition that we have. And from the first step, we said that, okay, so we recall the first step, we said that A0J, each of this solution of the initial equation is associated with a while group element. So for this simple example, we can calculate the spectra of this. And from the previous steps, let's look at like what's their eigenvalues of the Kovalevsky matrix. Okay, so here 2 and 4 we can easily recognize them. So because that's the degree of the Chavalit invariant of SO5, and they're constant. They don't depend on any. So which solution of the initial equation that we begin from, but there are other 4 eigenvalues. Actually, they depend on their solution of their of our initial equation. Okay, so let's see. We saw it before. So this is the number of eigenvalues of their Kovalevsky matrix is just a dimension of their Borel. Okay, the dimension of the Borel is a rank L plus the dimension of n, and the dimension of n is just the number. So this is just the number of the positive root system. Okay, so that means we can actually associate each of these eigenvalues that we don't know with a positive root of this Lie algebra. So we can do that. Then we put E alpha 2, for example, like this one. We named it the E alpha 2. This one named it E alpha 1, and this one E alpha E alpha 3 and the E alpha 4. In any case, let's just put it in a diagram. Then it looks like this. Okay, so we have 8 while group elements, and that means we have 8 solution for initial equation, because each initial equation corresponds to a while group element. So these are the while group elements, and we are looking at the positive eigenvalues of the Kovalevsky matrix, because at those points we may introduce new free parameters. Okay, so the first line says all the 4 eigenvalues are positive, and we know that the degree of Chavalit invariants are always there. So there's 4 plus that 2, that's 6 in total, 6 free parameters, and that's the dimension of their Borel. Okay, And we have there another wild group element. So these are the eigenvalues of the Chauvet invariants. And this is the total free number of free parameters. So from this simple example, we always observe that. So this is the rank of the Lie algebra. This is the dimension, actually, of the corresponding Brouillard seal associated with this W. Okay. And another thing that I want you to notice. So from this thing that we explicitly computed. So we see that this is 1, 1, 2, 3, and this is basically, if you ignore the sign, okay, in front of them, they are all 1, 1, 2, 3. It's just you need to change. So it's a shuffled around, and you change some sign. So after we take all this kind of information, let me give you theorems. So the theorem looks like this for other. So this is for other Fourier constant totalities defined on simple Lie algebras. So the initial equations always have this many solutions, and each of their solution can be obtained just in the way that I told you before. So you take a wild group element, you look at where the wild group element maps their positive co-roots into the negative ones. Okay, so the wild group elements will map some of their positive co-roots into the negative ones, and you take all of them out and you take their sum. And after you take their sum, you can write it in terms of your simple co-roots, and then you have a coefficients, and that coefficients will satisfy their initial equation. And if you, from this example, you see that if we know their A10, A20, actually we know other B20s, C10s, D10s, just like the equation, their pattern, their same pattern for the equation that I showed you before. So this is the first theorem that we can show. The second one is, so for the higher order term, we need to recursively solve this guy. And the information that I need to know is their eigenvalue of the Kovalevsky matrix. Okay, so the second solution is also nice. So each of these Kovalevsky matrix, the eigenvalues of a Kovalevsky matrix, it depends on their initial solution of initial equation. So equivalently depends on an element of their wild group. And we said that all of them are just the degrees of the Chauvet invariants. And there are, so the number of positive roots, that many, we don't know. And we need to calculate them. And so for each of those eigenvalues, we assign a positive root. So then their eigenvalues is just the height of this root. So we take the wild group elements, which corresponds to the solution of the initial equation, and you use that wild group elements, act on a positive root. After you act on the positive root, you take you just take their height.
So sorry, which positive root do you have to choose? Arbitrary.
Arbitrary.
So the answer will be the same for all of them.
Yeah, because I told you that. So for this guy, okay, so this Kovalevsky matrix associated with this wild group element. So this wild group element actually determine a solution of the initial equation, right? And there, so let's go back to this example. So two of them are constant. They don't depend on the solution of the initial equation at all. Okay, so that's the rank that many, and so we have 4 positive roots, and we have so this guy, all these guys, each of these is associated with a W, an element in the wild group elements, and each of this guy we can associate with a positive root, and you take any wild group elements, then that determines this guy. And we want
so
to
I mean,
calculate
if you change the positive root, you just exchange the order of this parenthesis, of this expression in parentheses somehow, right?
yeah.
Okay,
You actually so this result just tells you you're just shuffling them around, but you sometimes you make them like negative. Okay, so we only care about the positive eigenroots. We don't care about the negative ones, because the negative ones actually don't give us extra free parameters. So then so the theorem just says okay, you take any positive root, you use this Weil group element, act on it, and you calculate the height of this guy. So the height is what? So let's see, alpha equals ni alpha I. So the height L alpha is just the summation of ni. Okay, so your alpha is begins from a positive root, but this Weil group element may send you to a negative root. Then your height is negative. Okay, so your height can be positive, can be negative after the action of a Weil group element. And then this will give you the spectra of the Kovalevsky matrix, and that tells you, so on one side that tells you how many free parameters that you can introduce. Actually, the number of free parameters is the number of positive guys of this one, and the number of positive guys of this one, we know that's actually exactly the length of W, and exactly the length of W, that means yeah, so I will say this like this. Okay, so that's actually the dimension of the corresponding Bourgeois cell. So and also the third step, so the compatibility condition, and also the convergence of this. So the compatibility condition we need to show, and it's actually related with the structure theory of Lie algebra. And the convergence is actually shown already by Adler van Merbeck for the solution like in our kind. So we don't need to worry about. So after that, I showed like you other 3 steps in Kovalevsky-Penlevé analysis. And if we combine other analyses that we showed here, then we see that, okay, indeed, we can take any U and any W star inside their tau function, because here the number of free parameters we show that is exactly the dimension of the corresponding Bourgeois cell, and also we can match these two, like where these free parameters appear. So then this is our last theorem that says like how we compactify this guy inside their flag variety. So the conclusion is that the closure is the total of the flag variety. Okay, that also says that the other Laurent series solution of 4 constant totalities actually is exactly parameterized by the points in the flag variety, and also the so CL just says other spectral parameters. And I will make several remarks before we end. So the first thing I want you to notice is that other calculation that I performed, so other results that we get have integral nature. So that means what? That means so first we have to solve the initial equation, and the initial solution of the initial equation, they are integers. Okay, their singularity, so the exponents, they are integers. Their initial equation, solution of initial equations, they are integers. Their eigenvalues of a Kovalevsky matrix, they are integers. That means what? That means actually we don't need to do any of these things in a complex field. Actually, other things you can restrict to the real field. Even you can restrict to the rational field, because other things on the right-hand side, they are just polynomials. Okay, so that means if you begin with polynomial, and everything that I told you actually has an integral nature, that means actually this catches all the rational nature of this dynamic system. So that's the first thing. that I want to remark. There's second thing. So let me show you like why this result is actually, I mean, it looks very natural, but why it's non-trivial. So when we restrict this whole thing into the real field, actually in type A, a result of E.G. and Lauren. So E.G. Kudama, my advisor, and Lauren Williams says that there is a cell. So you can take the positive part of their flag variety. So that's so the solution of that part doesn't blow up at all. So that means in general you can't just you know, count the number of parameters and conclude that okay, this is their so this is the whole of it. And the second thing that we see here is that, now let me see whether I can show you here. Okay, it's not that convenient in this picture. But a second corollary of our result is this. So yeah, I could so it's kind of hard to see from here. But you see, let me try to show this. Okay, so there are 8 solutions for the initial equation, and there are 8 solutions that actually says that. So we want to know which smaller Brouillard cell that this solution will just get into. And if we just count the dimension, we may imagine that, okay, so the generic cell should intersect with the smallest Brouillard cell, right? That's the expectation, because the generic cell, it has the biggest dimension. So if we compactify it in a naive way, in the flag variety, so the biggest cell should intersect with the smallest Brouillard cell. But that's actually is not what happened. What really happened is there are only totalities that intersect with the smallest Brouillard cell is actually the tridiagonal totalities. So if you look at which cell intersect with the smallest cell in the flag variety, that has to be the tridiagonal totalities. That means actually the smallest one, not the biggest one. And the biggest one actually means,
sorry, what do you call the smallest Brouillard cell? Because as far as I can understand the definition, the smallest Brouillard cell should be just a point.
Yes, the smallest Brouillard cell is their point. So that means like you see, if you just look at their flag variety, okay, this is a very high dimensional thing, and the small Brouillard cell is some point in their flag variety, and actually their generic orbits would miss this point, and their only orbit that intersect with this point is their tridiagonal totalities. So that gives you another reason. You shouldn't.
It's really interesting because all in case of full symmetric total lattice, which also lives on flag variety, whenever your Brouillard cell actually meets the point, this point, then you almost for sure will the trajectory will almost for sure exit this point and go. All the trajectories of full symmetry go from the smallest point to the highest point.
Okay.
So whenever you have this point inside, you will never miss it.
Okay. So but for our calculation, actually it shows like you know, you have a lot of simplex leaves, right? And the generic one has the highest dimension, and the tridiagonal one actually has the lowest dimension. But the smallest Brouillard cell actually it's the lowest dimension simplex leaf will intersect with that very special point. Actually, the generic leaf will miss this point. So in general, you don't. So there if you just count the dimension, you will miss a lot of things. Okay, so I think my talk will just end here, and thank you all. for
Yeah,
attending.
Thank you.
Thank you.
Thank you very much. It was a very nice talking. The
Yeah.
timing was perfect, actually.
Okay.
Perfect timing.
All right.
Exactly 90 minutes, almost
Okay.
up to
Right.
5 minutes. Yeah.
Right.
Right,
So
so-
are there any questions or comments? I have lots of questions and comments, but definitely, well,
Actually,
talking
we
on-
are the only listeners now because Ira just disconnected and Junko
I
is here,
see,
but
I
I
see,
think
I see.
he already heard that.
Uh-huh.
I
So
see.
yeah.
Well, there are lots of
Sorry,
questions.
I'm
Actually.
hearing someone call me.
Okay.
Right. Do you have any comments, Junko?
I don't understand the talking since after 20 or 30
This
minutes.
is Junho
So
speaking.
Yes,
you
yes.
can
Yeah.
watch a little about this.
So sorry, Junho. Do you know where is Zhejan? He's
I don't
missing.
know.
Sure.
His working
From-
position is far away from me now.
I see. I
Okay.
see. So you actually
They are
meet
not-
him. Just let him know. We are
So
looking
you're-
for. We are missing him. Okay.
Okay.
So there are actually lots of questions, but they actually, as far as I'm concerned, I would definitely like to discuss this in person because there are lots of questions in connection between between your construction and this full symmetric order, because it seems that these two
Yes.
pretty similar systems have
Right.
drastically different behavior in many aspects. Well, probably one question which I really would love to ask is, do you know anything about the behavior of these chopping integrals which you described in case of full symmetric order, in full constant order?
Actually, so for these chopping integrals, all these things. So in type A, these are constructed by. I can see very limited things. Actually, that's one of their motivation that I do perform their Panevi analysis. Because Kovalevsky Panevi analysis, you begin with very little, so it just solve the equation like this is actually a thing that undergraduate students should do. But so I can see very little about chopping integrals. The first thing, like in type A, actually their method I showed is actually in type A. In type other types, so as type B, type C, type G, for example, they can embed it in type A.
Yeah.
So that means that you can use the same method to deal with them, but not type D. Okay. So type D you couldn't embed into type A. So that means so this is the original Heisenberg form that Organelli, Flaska, Singer they consider. So they couldn't deal with type D.
I just thought that Gehrman
and
Shapiro they actually spoke about symmetric order.
Actually, Gehrman Shapiro talk about like full constant to that.
Also full constant.
Actually, my understanding is actually their main thing actually they construct like full constant to that. So
actually their paper is pretty hard to read. That's one of the reasons I.
Yeah. So you need to use so they need to show that. So what they did is something like this. Okay. So in type A, I think some other guy I couldn't pronounce his name. So he find that every matrix in type A you have a normal form like this. So here you have something. Here you have I think it's 1, 1, 1, and here you have a kappa n to kappa 1, and here it's a symmetric kappa 1 to kappa n. So in type A, actually he found there's a canonical form, and then Gehrman Shapiro did is they generalized this to all types of Lie algebra.
Wasn't it Costan who found this kind of canonical form?
Actually their idea comes from Costan. It's called Costan cascade. Yeah, Costan cascade. And then they have to use their similar idea as chopping, but then they show that their chopping is the Poisson, their map is Poisson, and then this Poisson map to pull back, you get enough invariance. So, since you know, for example, there are lower dimensional coincidence. Okay, that means SO, for example, SL4 is isomorphic to SO6, and you can perform the chopping procedure either in type A or in type B. Actually, you get quite different integrals. And inside,
yeah, that's one of the interesting questions I really love to understand, right?
Yeah. In each of
actually,
them,
you can do. There are lots of questions. You can actually use some representation theory and try to pull back some integrable system from the space of representation to your.
Yes. So
yeah,
that's actually representation theory side. So here is actually a quite a curious thing and interesting, I think. So you see, actually, I actually showed you two methods to solve four constant totalities. One is the tau function, and the construction of the tau function actually depends on the fundamental representation of the Lie algebra and the Lie group. Okay. The other one, Kowalewski-Panlevi analysis, actually, it doesn't depend on the representation at all. So it depends on it actually depends on the structure, underlying structure theory of the Lie algebra. So that means, for example, this kind of system you write down, no matter it's LS4 or SO6, actually you get the same thing. So it doesn't depend on the representation at all. So that means that the integral that we care about, so how to construct the extra integral we care about, should somehow, you know, hide inside this system of equations.
Yeah.
And actually, I think somehow, you know, when we calculate the spectra of Kowalewski matrix, and we know that we have to introduce 3 parameters. And these 3 parameters should have some meaning. And that's, I think that's one thing that should be in a dig. But since this calculation is already like you know, a disaster.
Yeah, I really don't understand how you can compute Kowalewski matrix. Because I mean, it looks pretty huge, to say the least.
Yes, so that's that's yeah, that's the thing that it's remarkable, like 4 constant totalities. I mean, for any other system, I don't know, I couldn't imagine like how you how you can do this. But for 4 constant totalities, actually, I mean, not only you can do this, you can have a like very nice explanation, you know. I mean, this kind of a formula you normally you couldn't expect. Yeah,
I really would love to know the details, but definitely not today. So thank you very much for your very nice talk. It's a pity that not many people, but some people, I mean, there are now only 4 of us.
So we are the happy few.
Yeah, thank you very much. And I don't know, but yeah, so next time, I don't know yet who we're going to listen to next time, but I'll send the information by Saturday, definitely. Okay.
Thank you for the invitation. And also, like you know, I would like to either you come to Beijing, or sometime I have a chance to go to Moscow, so we can, you know, discuss a lot of other things.
We hope to get to Beijing this fall. I just don't know when. We don't yet know when, but yeah, sometime this fall, maybe even summer.
That I mean, summer would be great, because yeah, and also like so a moment ago, like we said Junhu is not in Beijing.
I'm in Beijing. I'm in Beijing now.
Oh, yeah. I see.
I see. 我看你这个出国出境申请，你是 Are you going to Moscow? Apply to.
So it's not decided yet. Like nothing is decided yet.
So your 所以你这个出国申请体系看很弄。
So I
Okay.
don't know where I will end up with. So but yeah, but I really like. I mean, last semester, it's because of the COVID-19 scene, we didn't find time to discuss it, and also like we're kind of busy because I taught like I had to teach a class. That takes me a lot of time, and many other things were busy. Yeah, but hopefully in the future we can find more time to
Yeah, I
discuss.
really hope so.
Yeah,
really hope
KP,
so.
TOTA, and many other things.
Sure.
Yeah. Mhm.
Okay. So thank you everyone. And I think since we are not the hosts of this, we just leave this conference and then the administration of the independent university will take care of the recording. Thank you.
Thank you.
Okay.
Thank you.
Okay.
Yeah, bye.
Okay,
Bye.
goodbye.